factors and the GCF. Does anyone remember what GCF stands for? Raise your hand. Yes, Turner? Greatest common factor. So is factor a big part of this lesson? Yes. Okay. So we're going to go through some, like I said, review, and hopefully it all comes out from the recesses of your mind if it isn't out front. A factor is a number. This is deep, guys, so please get this down. Is a number that is being, and this is a critical part, multiplied. That's what a factor is. It's a number that's multiplied. That is being multiplied. That means it's one of the numbers that you put when you're doing a multiplication problem. That's a factor. That's all it is. Do you remember, and I hope you remember because it wasn't that far back, on your test, you did a lot of multiplying, correct? Did you do a lot of multiplying? You dealt a lot with factors. But when we use that term factoring, it's basically not the inverse of multiplication, it's the reverse of multiplication. And you're like, huh? We're going to get more into that as we get toward the end of the lesson and into the rest of the chapter. But that's basically what we're doing in this chapter. Okay, we're going to look at example number 1. I'll go ahead and turn. You guys okay with that? Example number 1. It wants me to find the factors of 72. So I'm using the number 72. And basically what they're asking, what are the numbers that you can multiply to get 72? So there are always two easy ones, by the way, that you should be able to get right away. And this is how I do my work on these problems, because you'll have to do this on your homework. Can I multiply 1 by 72? Is that going to get me 72? So we would say that 1 and 72 are factors of 72. Does that sound okay? Does any other number go into 72? I know that. 2 goes into 72. Does anyone know what 2 times what equals 72? 36. And so I'm putting it out to the ends because I'm going to work my way inside. And this is actually a good review for divisibility rules. How do I know that this number is divisible by 2? Does anyone know what that rule is, Matt?
It ends with an even number.
Yeah, it ends with an even number, or it is an even number, so 2 goes into it. Does 3 go into this number? And if so, what's that rule? Does anyone remember the rule of 3 is? How do I know this could be evenly divided by 3? Lucy? Yeah, you add these two digits together. What's 7 plus 2? 9. Is that 9 divisible by 3? So the whole number is divisible by 3. Does anyone know 3 times what equals 72? Think of time, days, hours. Jenna? 24. Okay, good. So 3 times 24 is 72. Does anyone know what the rule? Does anyone know what the rule for 4 is? There's actually a couple ways you can put it. It's a little tougher. Jack? Okay, yeah, that's one of them. But what if it doesn't end with any 0 or just 1 0? Here's how you can figure it out. Can this be divided by 2 twice? Like, can I divide this by 2 and then divide by 2 again evenly? It's divisible by 4. Does anyone know 4 times what equals 72? 18. I don't know if I'll have enough space here. Gotta see if I can squeeze in here. Is it divisible by 5? No, because the number has to end with a 0 or a 5. So not by 5. By 6. What's the rule for 6? I like 6. Carson, say it again. Good. If it's divisible by 3 and 2, then it's divisible by 6. So 6 works. And if you know your multiplication facts, you should know 6 times this equals 72. 12, yeah. I had the awkward pause there. 12. 6 times 12 is 72. 7, does it go into it? No, you can already tell if you divide it by 7, you'd get a remainder. 8. Multiplication facts say yes. And let's see here. 8, 9. Nothing else goes into it. Once you get into two numbers that are either next to each other, consecutive, like 8, 9, or they're very close and you know no other number fits, you're done. Oh my. How many factors are there of 72? A lot, right? Just a lot, and you can count them up and get that. I'm thankful we're not going to have to do this in class. We're not going to have to do this the whole lesson. But can you figure out the factors of 72? Yes. If I had to give you some problems, you can figure it out. Okay. Let's look at page 561, number 5. 561, number 5. And they want you to factor out the number 4. So please don't hurt yourself doing this one. The factors of 4. Well, I start with the easiest ones. What are they? 1 and 4. Are there any other factors of 4? 2. And you would just say it. You just say 2 once. You don't say 2 and 2 because 2 is the same thing. Okay. So any other factors of 4? Nope. That's all you had to put. Good with that? Okay. Why are we even doing this? There's something about these numbers that we want to classify them into. And this is really getting into the meat of the lesson. So, do you guys remember the two terms prime and composite?
I remember prime.
Prime, okay. And then maybe composite's a little hazy. Maybe neither of them are clear. It's a prime. Anyone remember what a prime number is? It's a good number. What's a prime number? Emery?
Number that can only be multiplied by 1.
Okay, good. That's actually it. I'm going to give you a technical definition because then I get these questions that are like, but what about this number? Okay. It is, so a prime number is a whole number. So it's a specific type of number. And then we say greater than 1. So can it be a negative number? If it's greater than 1, can it be negative? Can it be 0? Can it be 1? No, because 1 is not greater than 1. Whose only factors are 1 and itself. So what Emery said there are 1 and itself. All right? So that's a prime number. So have we looked at a prime number with 72 or 4? Are either of those prime numbers? No, because did they have 1 in itself being a factor? Yes. But were there any other factors? Yeah. It's not prime. Therefore, if it's not prime, it must be composite. And I was debating on how to put this. I'll just put it like this. A whole number. So are we talking about fractions and decimals here, by the way? No, we're talking about whole numbers, which is a critical difference between those numbers. It's a whole number that is also greater than 1. So we're talking about positive numbers and not 0 and 1. And we could say that has more than 2 factors. So all those numbers that have more than 2 factors, those are called composite. Okay, write that down, and then we're going to look at some numbers to see if we can distinguish. And I just thought of something. I apologize. We're not getting observed in this class. It's the next class because I got my times wrong. I thought it was this one. So you guys can do whatever you want. No, you guys are doing well. Okay, so no one's going to come in, I don't think. No, I don't know. Okay, go ahead and list out the numbers starting with 2, 3, 4, 5, 6. Go 7, 8, 9, 10. Just list those numbers out. And can you guys give me the factors of 2? What are the factors of 2 real quick? So I'm going to put here, I'll put 1 and 2. I'll put in that order. What are the factors of 3?
1 and 3.
1 and 3. Of 4?
1, 2, and 4.
Yeah, 1, 2, and 4. We did that one, right? So I hope you got that one. What are the factors of 5? 1 and 5. What are the factors of 6? 1, 2, 3, and 6. And go ahead and do the rest. Don't say them out loud. Get those factors of 7, 8, 9, and 10. All right, Abby of 7.
1 and 7.
1 and 7. Lily M of 8.
1, 8, 2, 4.
Good. 1, 8, 2, 4. Jackson of 9.
1, 3, and 9.
Rosalind of 10.
1, 3, 5.
Okay, so if you're able to do that, you should be on a good path for these questions. Like, what are the factors of 10? You just list them out. Okay, let's look at prime and composite. Is 2 a prime number? Based on our definitions, is it a number greater than 1? Mm-hmm. Does it have only 2 factors, 1 in itself? Yep, this is prime. What about 3?
Yes.
Prime or composite?
Prime.
Prime. Everyone. 4. Composite. Matt, why is 4 composite?
Because it has more than 2 factors.
More than 2 factors. Good. It has one in itself, but it also has another one too. Jack, 5 is prime or composite? Prime. Lily, G, is 6 prime or composite? Composite. Why is it composites, Emery? Why is 6 composite? Yes, so according to the definition, it's composite. And that's because it has more than 2 factors. It has more than 1 in itself. So it has a 2 and 3. Okay, and so we have all these here. Prime, composite. Composite, composite. What's the next prime number? After 10. 11. After that? 13. After that? 17. After that? 19. After that? 23. And you can keep going. How many prime numbers are there out there?
Infinite.
Infinite number. It's really hard to find them after a while, but they're infinite. Yes, sir. Oh, yes. Good question. All right. Notice that I didn't even do 1. Because is it, according to those definitions, is 1 greater than 1? No. And another way you can kind of think of it, what are the factors of 1? 1. So it only has 1. It's a special number. So we say 1 is neither prime nor composite. Okay? And then 0, that one's an interesting one. Yeah. Negative numbers, so listen carefully, guys. Negative numbers are neither prime nor composite. But later on, we're going to see what do you do if you do have a negative number? Like, how do you break it down into its parts? So we're going to talk about that. Good questions, I think. Very good. Okay. Here's a note I want you to get because this is critical to the lesson. Every composite number, so every number that has more than 2 factors, can be written with what we call prime factorization. Just kind of listening to myself say prime factorization sounds like something bad. You've been prime factored. Oh. That is, you're going through prime factorization. Ugh. It's actually very good. I love prime factorization. I love it. I love it. I love it. Because it actually applies to this chapter, geometry, algebra 2, pre-calc, calc, and then anything else you want to take after that. Prime factorization is really helpful because it makes things simpler. Okay? And once you get more comfortable, once you guys get more comfortable doing it, you should get quicker, and you're not going to notice the long process that you might think of at the beginning. Okay, we've done this before, by the way. Example number 2 on 559. It says, find the prime factorization of 140. So what I want to do here is I want to use one of 2 methods. And we've talked about this before. Do you guys remember the factor tree? or we call it division by primes. Factor tree or division by primes is going to be sufficient. So I'll do the factor tree first. What two factors give me 140? Any two factors, it doesn't matter. Just don't pick 1 and 140 because that gets us nowhere. Yes? Good. 14 and 10. Okay. I'm going to keep going with 14 because 14 is not a prime number. I stop at prime numbers. So what can 14 be broken into? 7 and 2. Is 7 a prime number? So I'm done with it. Is 2 a prime number? Yep, I'm done with it. So I stop at the prime numbers. If either one of those was not prime, I keep breaking it apart. 10. 5 and 2. Is 5 a prime number? Is a 2 prime number? So we're done using the factor tree. So the prime factorization of 140 is 2 times 2 times 5 times 7. And does anyone remember from last chapter if I can write that in a little bit of a different way? Slightly different. Nothing too major here. Claire? Not completely. Oh, sorry. Yeah, you can. You can completely say. 2 to the second times 5 times 7. So either one of these is going to be acceptable. Listen very carefully. On your homework, they're going to say, factor this number. Do not use exponents. Which answer is the only acceptable answer? Top one. If it doesn't say not to use exponents, you can use either one of these. Do you understand me there? There's a reason why we're doing this. You'll see that more later. But you got to be able to listen to those instructions. Okay. Wow, that wasn't that bad. Okay. I forget who asked, but someone asked, was it you, Carson, or Brian, about negative numbers? Yeah. Brian? Okay, example number 3. They gave me negative 150. Oh, man. Is that prime or composite?
Neither.
Oh. Wait, but why is it not prime nor composite?
Because it's not greater than 1.
It's not greater than 1. But we can still factor it, just like you can with the other problems. And sorry, I forgot the division by primes. I'll do it here on this one. What you're going to do is, if you're going to do the factor tree, just break it down into negative 1 and 150. So you're done with that. You're done with the negative sign. It's going to go in your answer, but you don't have to factor that anymore. Can I factor 150? Yes. So go ahead and do that. Someone help me out. What would you do? Nate. 25 and 6 works, because 25 times 6 is 150. Should I circle either one of those? Nope. Maggie, what would you do next? 5 times 5. Can I circle those? Yeah, I'm done with 5 and I'm done with 5. Lily G, what happens to 6?
You can break it down to 2 and 3.
2 and 3, and both of those get circled. Okay, so here, if I'm factoring negative 150, this is what I would write for my answer. Negative 150 equals negative 1 times 2 times 3 times 5 times 5. Or 5 squared, if it didn't say don't use exponents. This is your prime factorization. Okay? Is that all right? Is negative 1 a prime factor? Technically, is it a prime factor? No, but you can still deal with it and just get rid of that negative 1 for a little bit. Okay. The other way I was talking about for finding the prime factorization, so we still have that negative 1. I do upside down division. I'm telling you, this, for bigger numbers especially, makes it so much easier. No more trees. This is just a big cake that's upside down. Yeah. They used to call it upside down cake method, so I don't know why. I call it the Leaning Tower of Pisa because it falls over. All right. What you can do is just say, what's a prime number that fits into 150? What's a prime number? 2. 2, you can use that. 2 goes into 1, no times. 2 goes into 15, 7 times, right? With the remainder of 1. This is actually short division. And if you don't know how to do short division, I feel sort of sorry for you because it makes it so much easier. 2 goes into 10, Wait, is 2 times 75 150? It is. Okay, what other prime number can go into 75? 5. 5 goes into 7 once with the remainder of 2. 5 goes into 25 5 times. You can go with 5 again 3 times. Did we get the same thing? Yep. No?
We don't have negative 1.
Do you remember what I said about negative 1? No. We already had it at the beginning. Like they both had negative 1 at the beginning, and then 2 times 3 times 5 times 5. Okay, so if you don't know how to do that yet, I honestly strongly recommend you start doing the division by primes, and that's short division. Okay, and you're like, short division? That doesn't seem short to me. It is. Okay. All right, so you can do either one. I'm okay with either one, but try to get comfortable with the division by primes. And that takes a little bit more mental math. Actually, you know what I found out? I was reading about a study in math, and they were saying this. If you're using your fingers to count, you're actually hindering yourself from getting better at algebra specifically. Why? Because what happens is you're trying to make something very concrete when it can be something more, how do I want to say this? It could be more, not complex, but, mental, but we'll use complex. It's something that's a little more complex that you can't always like put down on paper. It just makes you stay at the concrete, we call it, and not deal with that's it, abstract thinking. You know, abstract. You've heard that maybe in English or something. So try to avoid using your fingers. So this is what I do. I get rope. I tie one hand. Then someone else can help me out. And then when I'm doing that, I cannot use my fingers. I have to look into the abstract world of thinking. Okay, and try it out. And then you have to untie and then write things down. It's really hard. Don't do that. But really, duct tape your hand. That would hurt when you take it off, and it may hurt when you put it too tight. But what I'm trying to say is try to avoid using your hands and fingers. Can you guys do that for me? For your own good? Don't do it for me, actually. Do it for your own good. Okay. Work it out, but try not to use fingers to add, subtract, multiply, divide. Try to get away from that. Practice makes better. All right. Page 581. Wow, that's not what I wanted. 561, sorry. Do number 8 on 561, number 8 says, state whether each number is prime or composite. So you're going to say it's prime or composite. If the number is composite, find its prime factorization. So number 8. So what you're doing on that, they give you the number 39. All right, is that a prime number or a composite number? It's composite, so you just write the word composite. That's one answer. And then, since it's composite, you can break it down into its prime factorization. It's like, what goes into 39? Yep. 13 and 3. 3 times 13. And are those both prime? So what's the prime factorization of 39? 3 times 13. That's all you have to do. Yeah.
What would happen if we tried to use a decimal number in that?
You couldn't do prime factorization because we're talking about like whole numbers or even integers, but not decimals or fractions. Actually, what you could do, now that you bring it up, good question. You can do the prime factorization of the numerator and the prime factorization of the denominator, and then cancel any common factors. So you could do that, but not just a fraction or decimal. If it's a decimal, make it into a fraction, then do that. Okay, number 7 on that same page. Do number 7. If it's prime or composite, the number is number 7, and they're asking about 89. Prime or composite for 89. So based on what I'm doing, does 2 fit into it? Does 3 fit? Does 4? Does 5? Does 6? Does 7? Does 8? Does 9? Does 10? And there is actually a stopping point, and I'm actually going to give you the shortcut in a couple chapters because it's too complicated to go over. Do you guys remember square roots? Do you know what square roots are? Kinda, maybe. It's asking you what number times itself equals the given number. The closest square root to 89 that I know automatically is the square root of 81. Do you guys know the square root of 81? 9, right? So I only have to test this up to, I go all the way up to 9 and then try out 10, which obviously doesn't work. And if I tried all those numbers and they don't fit, there's no numbers that fit into that. So what is this called? It's a prime number. Prime number. You guys okay? So I'm not giving many of these, so don't feel like you have to do this too much. But yeah, there is a trick on that. I wish I could go over it. Okay, anyway, let's keep going here. Example number 4. Now we're going to look at monomials and see if we can factor those. Is that even possible? A monomial? 45x cubed y squared. All right, listen up, please, because this is getting to almost the very last part of what you're doing in this lesson. Okay, what I want to do is I want to get the prime factorization, that's basically what I'm asking, of this expression. So you're like, what do I do with those variables? Just deal with the numbers for now. What does 45 break into? 5 and 9. And 5 is a prime number, but 9 is not. So I get my 3 and my 3. So right now I have 3 times 5. That's for the number part. And ready? The variable part is not that bad. Okay, I don't know what x is and I don't know what y is, but I know I can factor them out. All I have to do is this. Times x times x. Times x again. There are 3 of them. Times y times y. That's it. That's factoring it. Break it down into multiplication. Remember, what does factor refer to? What operation? Multiplication. So is this a multiplication problem? Yeah, and it's just multiplication. That's it. No powers, no nothing. No, don't leave it with powers. Okay, good question. When they say to factor this, I do not want exponents. Why? Because it's almost like you just did 3 times 3 times 5, and then you did nothing with that. No, they want to show a strict multiplication problem. So, good question, but make sure you follow that. Whew. That was the first half. I'm just kidding. We're on the last part here. Okay. Do on page 561 again. I'm sorry, we're going back and forth. Factor out number 10 completely. It says factor each expression completely, and then they say this: do not use exponents. So, Mr. A, can I just leave it with that? No. But now, and the reason I'd be discouraged actually, because I'm like, it's right there. Sorry? Wonder no longer. When you get there, you'll find out. Number 10 here. Okay, Matt, the number can be broken down into what? 2 times 11. Emery, the rest of it.
Times m times n times n.
That's done. We've factored it completely. Okay, last part here. And notice all we've really been dealing with, factors. All we've been dealing with is factors. Now we're going to get into the greatest common factor. And I went over this with the 7th graders not too long ago. And one of the biggest things people do with greatest common factor is they mix it up with least common multiple. They're not the same thing. So we're not even talking about least common multiple. So just do what we're doing here on these problems. Okay, let's look at example number 5. And let's see if we can figure out how to find the greatest common factor. Okay, so we're talking now about GCF. And for some of you who don't know that, greatest common And yeah, we're going to say factor, but you can break it into factors to get that one factor. And you're like, okay, we'll see what that is. Okay, Jack, do you have a question?
Yes, sir.
Yeah, go ahead.
Why did we do 1 and 22?
Did I do 1 and 20? I thought I did 11 and 2. 2 and 11. Is that what you mean? Oh, sorry, you want to write prime factors, so you wouldn't use 1 and 22 because 1 and 22 are not prime. Okay, so this is example number 5. And once we get this down, we should be able to work out the lesson. Okay, what are the 3 numbers they want me to find the GCF of? Lucy, give me the numbers. And sorry? 180. Okay, 180. So what you're going to do is you're going to break these into the prime factors. Just break them down into the product of prime factors. And I'll give you a little bit of time to do that. Hopefully you can... Oh, I don't need that. Oh. Sorry. Okay, Lucy, can you give me the prime factorization of 54, please? Please give it to me in order.
2 times 3 times 3.
Okay, 2 times 3 times 3 times 3? Okay. Rosalind, give me the prime factorization of 63. Okay, and then last one, 180. Autumn of 180. Oh, sorry, can you give it in order? Starting with 2. I have two 2s, then I have a 3, and a 5. Okay, so do you have those prime factorizations then? Okay, I want to find the GCF, the greatest common factor. Okay, so in that word greatest common factor, and I'll abbreviate it, you're dealing with what? Good, factors. And they're common. That means that they're shared among those numbers. And you're eventually going to get the greatest of those shared factors. Okay, so this is what I do. Are there any factors that all 3 of these share? Can anyone tell me what factors they all share? They all share, Jenna.
Well, technically it's the 3 of them.
Okay, don't they all share a pair of 3s? Anything else that they share in common?
No.
Okay, they all share these factors, so they're common factors. And what is 3 times 3?
9.
So the GCF of these 3 numbers is 9. That's the greatest common factor. It's the greatest common factor. I mean, it's what it says it is. Sorry, are you telling me to come over there? Okay. If you can do this next one, you are set. On page 561, last problem for you guys, number 16. Give me the GCF of those 3 monomials. Mr. Ava, what do you do with those variables? The same thing you do with those numbers. Uh-oh. Oh my God, sorry. Okay. And by the way, you can check yourself on these. You're just like, okay, it's 2 times 3 is 6, times 5, that's 30. That works. 2 times 3 is 6, times 7 is 42. 2 times 3 times 3 times 3, you can go at 3 times 3 first, times 3 is 27, times 2 is 54. You can go in any order. Okay. And 3 A's. All right, just look at the numbers. Out of the numbers, what are the common factors? Just out of the numbers. What do they all have in common? They both share, or excuse me, they all three share 2. What else do they share? They all share a 3. Anything else? Any other number that they share? Okay, no other number. One has a 5, one has a 7, one has a couple other 3s, but they don't share those in common. Now, how do you deal with those variables? The same way you dealt with the numbers. Do they share any variables in common? They all three share 2 A's in common. Okay? So, the greatest common factor of those 3 monomials, the GCF, is Maggie. Good. And you'll write it 6a squared. You'll write it in its multiplied form, 6a squared. How many of you got that? Whew. Okay. This lesson is unique because there are a lot of little sections. So this section says find the factors, tell me if it's prime or composite, factor it out completely, and then the last part, find the GCF. Okay, your homework tonight is 19 to 45 odd. If you can start working now, you should be okay. Oh. Goodbye, sir.